So in today's lecture, we're going to talk about things moving in uniform circular motion. That is, we're going to look at the physics of things moving in perfect circles. So hearing this, you might think, well, when are things truly moving in perfect circles? And that's a reasonable question to ask. But the reality is, we can approximate the motion of an object that's turning as being part of a perfect circle. And because of that, we will find that uniform circular motion is actually pretty useful to us. So let us begin by defining what uniform circular motion actually is, so that we may work with it more precisely. So definition. So uniform circular motion is the motion of an object, traveling at a constant speed. So traveling at a constant speed on a circular path. So now let me draw a quick picture for us to look at while we discuss, things moving along a circular path. So if I zoom out a little bit, right, we have a circle. All right, let's say the center of the circle is here. Let's assume that this circle has a radius of r. Right. And so uniform circular motion at every single point as the object travels around its circular path, the trajectory or the velocity of the object is going to be tangential to the circular path at every point. So this, and this. Right. So way back in our first week, we talked about average speed. So the average speed is the distance traveled by an object divided by the time it takes that object to travel that distance. Right? We can use this to figure out how fast an object is traveling in uniform circular motion. So if the radius of the circle is r, right, like I've shown here, then the circumference of the circle is 2 pi r. So the circumference of the circle, I'm going to call c. Right, that's equal to 2 times pi times the radius of the circle. Right, that's the distance it takes to go around the circle once. Right, it's equal to this value here. So furthermore, let us call the time it takes the object to travel around the circle once the period, so t. So the time it takes the object to travel around the circle once, we're going to call it the period t. So t, called the period of the motion. And we're defining that to be the time it takes for one revolution. Right? So it's how long it takes the object to go around the circle once. So by knowing these two things, our average speed, in uniform circular motion can be calculated, right? Because if the object travels around the circle once in a time t, then the average speed of the object is given by the distance traveled. So the average speed, v, is given by the distance traveled divided by the elapsed time it takes to do that. Right? But if we go around the circle once, then we will have traveled a distance of 2 pi r. Right? And then the elapsed time is just our period t. So this is going to be important. The magnitude of the velocity as we go around the circle at any point in time, right? If we're undergoing uniform circular motion, this velocity is going to look like this. So this is our first main result from this chapter. All right, so if the object were to stop traveling in a circle suddenly, then the speed with which it will travel in a straight line is this speed v, right? And so let's look at an example. So this will be example 1. Example 1. So let me scroll down a little. So example 1 says that the wheel of a car, has a radius of 0.29 meters. Right, or 29 centimeters, but we're going to keep it in meters. And is being rotated at 830 revolutions per minute. Revolutions per minute, right, which we are going to abbreviate as RPM. Right. So it's, being rotated at 830 revolutions per minute on a tire balancing machine. A tire balancing machine. So the problem wants us to determine the speed in meters per second. So determine the speed. In units of meters per second, at which the outer edge of the wheel is moving. The outer edge of the wheel is moving. Right. So let's write down what we know. So we know that the speed that something is traveling in while undergoing uniform circular motion is 2 times pi times r, all divided by t, which is the period of the motion. So how long it takes to go around once, right? So the problem is asking us for the speed at which the outer edge of the tire is moving. So we're trying to find this, and we know the radius because that's given to us, and 2 times pi is just a number. So we've got to do a little bit of work in order to find t. So the time t for 1 revolution, t is time for 1 revolution. Right, remember that's our definition. So we know that this tire rotates at 830 revolutions per minute. Revolutions per 1 minute. Right? And we know that there's 1 minute in 60 seconds. And so the units of minutes cancel out. And then we get an answer of 830 over 60. Right? Revolutions per second. Right, but this is just 13.83. 13.83 revolutions per second. Right, and we're looking for the time for 1 revolution. So in our case, the time is going to be 1 over 13.83 revolutions per second. So this is going to be equal to 0.072 seconds. Right, where I've already sort of implicitly done, the conversion. So this is really in units of, seconds per revolution. But since t is defined as the period for one revolution, right, the time it takes to make one revolution, we're implicitly multiplying by one revolution. So that gets canceled out. And then we're left with a period of 0.072 seconds. Right. So using these two pieces of information, the radius, right, which is 0.29 meters, using that radius and the fact that we know how to calculate the speed of an object moving in uniform circular motion, right, we can actually calculate how fast the outer edge of the wheel is moving, at this speed. So we have that v is equal to 2 pi r over t. Right, so we have 2 times pi times r, so it's 0.29 meters. And we're dividing by the period, so 0.072 seconds. Right, and we do this, we get that the outer edge of the wheel is moving at a speed of 25.2 meters per second. 25.2 meters per second. And this is our answer. So in this case, if there was like a little pebble that was attached to the outer edge of the tire and it managed to fly off, as it was spinning at the speed, then it would fly off with a speed of 25.2 meters per second. Right. So next up, we're going to look at centripetal acceleration. Right, now that we've finished with that example. So something that is deeply related to uniform circular motion is the concept of centripetal acceleration. So we figured out how fast an object must be traveling if it's traveling under uniform circular motion, right? That's, v is equal to 2 pi r over t. But we also learned in the first 2 weeks of this course that velocities are only changed when the object experiences an acceleration, right? Even though the object is traveling around the circle with the same speed, which you can think of as like the same magnitude of velocity, the direction of the velocity is changing, right? How else could this thing move in a circle? So there must be some acceleration present in order to keep the object moving in a circle. And we call this acceleration the centripetal acceleration, right? And so it has a magnitude of, call it AC for the centripetal acceleration, and has a magnitude of our speed squared divided by the radius. All right, so this here, this bit here, this is the magnitude of our centripetal acceleration. And its direction is towards the center of the circle. Towards the center of the circle. Right, so if we got a circle and an object is traveling at uniform circular motion around the circle, let's say, then, if our object is here and it's traveling like this, then its velocity will be tangential to which path, right? But the centripetal acceleration will be directed from the object directly towards the center. So this is our centripetal acceleration. So let's look at another example. All right, so example 2. This one's pretty short. Example 2. So in this example, a car is moving on a circular path. Moving on a circular path. A radius 10 meters. A radius 10 meters with a speed of 20 meters per second. Speed of 20 meters per second. So the problem's asking, what is the centripetal acceleration? So we know the direction is always pointed towards the center of the circular path. But so this is really just asking us to find the magnitude of the centripetal acceleration. So we know that the speed of this car is 20 meters per second. And we know that the radius of this track is 10 meters. So the magnitude for our centripetal acceleration, which is v squared over r, it's going to be 20 meters per second. We're going to square that, divided by the radius of the circular path, which is 10 meters. This is going to be 40 meters per second squared. So the centripetal acceleration magnitude is 40 meters per second squared. Just like that. Right. So last week, we learned about Newton's 3 laws of motion. More specifically, we learned that the second law relates the net force acting on an object to that object's net acceleration. Well, it turns out that it works both ways, right? If there's a net acceleration on our object, then that can only mean that there's a net force acting on our object. So in the case of uniform circular motion with its centripetal acceleration, we call this force the centripetal force, very creatively. And it has a magnitude of the mass of our object times the centripetal acceleration. So let's write down centripetal force, right? We talked about the acceleration, but now we're talking about the force that causes that acceleration. So this is from Newton's second law. And so we have a magnitude for this centripetal force. We call it Fc for centripetal. This can be equal to the mass of our object times the centripetal acceleration of our object. But we know that the centripetal acceleration of our object is v squared over r. And so this is the magnitude for our centripetal force that lets things move in uniform circular motion, right? And just like with the centripetal acceleration, the direction for this force, direction is again towards the center of the circle. Right. So it's important to note here that the centripetal force is not a new force. So any force that is always directed towards the center of a circle that an object is moving in can be called the centripetal force, right? So this can be the gravitational force of attraction between a planet and its host star. It could be the tension in the rope of a ball being swung around in a circle above your head. Or it could be the normal force of a curved highway exit road pressing up on the tires of your car as you go around it. So any force that can consistently point towards the center of a circle, or any force that has a component of force directed towards the center of a circle, can be a centripetal force. So let's look at some more examples. So this is example 3, I believe. Example 3. Example 3. So example 3 says that one end of a rope, so one end of a rope of length 3 meters, is connected to a ball, of mass 2 kilograms, and the other end is held by a person. And the other end is held by a person. Right? They rotate the ball in a horizontal plane. They rotate the ball in a horizontal plane. Right, so they're just swinging the rope and the ball above their head and pretend like it's just, the circle is parallel to the ground. So they rotate the ball in a horizontal plane with a velocity magnitude of 5 meters per second. So the problem wants us to find the tension in the rope. So find the tension in the rope. Okay. So the top-down view of our problem, we have circle, right? There's a person at the center, so this is the top-down view. Like we're looking at this person from a helicopter. So the radius of this rope is 3 meters. And there's a ball at the end of the rope that has a mass of 2 kilograms, right? And it's just being swung around. And so we're trying to find the tension in the rope. So in this case, the tension in the rope is going to be the centripetal force required to keep this ball moving in a circle, right? Because if you were to just let the rope go, then the ball would fly off and it wouldn't be moving in a uniform circular motion. So the tension in the rope is entirely responsible for the centripetal force in this problem. And so we know that the centripetal force is just the mass times the centripetal acceleration, which is v squared over r. And we know all this stuff. So we know that the mass is 2 kilograms. We know that the length of the rope, or the radius of our circle, if you want to call it, is 3 meters. And we know that the speed that this thing is being flung around with has a magnitude of 5 meters per second. So plugging all this in, right, we have the mass, which is 2 kilograms, times our speed squared. So it's going to be 5 meters per second. We're going to square that. And we're going to divide all this by the radius of our rope, or 3 meters. Right. Well, in this case, we get a tension force in the rope, which is a tension, if you want to call it, of 16.7 newtons. 16.7 newtons. So that's it for that example. So now let's look at something a little bit more complicated than this. So let's look at example 4. So example 4. So example 4 says, at what maximum speed, Can a car safely negotiate? Can a car safely negotiate? Admittedly weird word here, but whatever. A horizontal unbanked turn. A horizontal unbanked turn. So it's flat ground. You're just driving in a circle. So a horizontal unbanked turn with radius of 51 meters. The radius of 51 meters in dry weather. In dry weather. So that's going to have a coefficient of static friction between the tires of the car and the road of 0.95. And icy weather where our coefficient of static friction between our car and the road is 0.1. Right, so it's much less. Okay, so let me scroll down a little bit. I'm going to draw some pictures. So first, I'm going to draw a top-down view. There we go. So we have our circle. We have our car driving around the circle. Might be driving with a velocity v. Yeah, that doesn't look very tangential, so there we go. So car is moving around, right? And in this case, the thing that's going to be providing our centripetal force, in this case is actually going to be the static friction between our tires and the road. It's going to be our frictional force, right? Because as the car goes around this bend, it wants to slide outwards like this. And because the car wants to slide outwards, the static frictional force wants to oppose that motion, so it's going to point towards the direction of the circle. So in this case, the static frictional force is our hero in this problem. So this is a top-down view. Top-down view. Right, then over here, I'm going to draw side view. Like this. Okay. So if this is our circle now from the side, and here's the center of this circular path, and then our car is right here. Draw this little box. Right, and there's a couple forces acting on this. So there's the normal force pushing up. It's the force of the ground pushing up on the car. You have the weight of the car pulling it down. Right. And last but not least, you have the static frictional force of the car pulling it towards the center like this. Static frictional force. So these are our pictures. So, looking at this, at the right picture, the side view, we don't want any motion in the y direction, right? We don't want this car leaving the track. We don't want it rising up. So in this case, you see that we don't want any motion. So no motion. In y direction. All right, so this implies that our acceleration in the y direction will be 0. Right. And so now if we look at the sum of the forces in the y direction, this case, the sort of axis that I'm using is we have y going up. And then our x-axis is just horizontal, like so. So if we're looking at stuff in the x or the y direction, so the sum of our forces in the y direction, it's going to be equal to the mass times the net acceleration of our car in the y direction. But we've already said that has to be 0, so the right-hand side has to be 0. Which means that the left-hand side, which is the sum of the forces, has to be equal to 0 also. So we have the normal force pointing in the positive y direction, so that it's a plus sign. So the normal force pointing up. And then we have the weight, mg, pointing in the negative y direction, so it gets a minus sign. And those are all the forces acting on our car in the y direction. So that's going to be equal to 0 newtons. And we see that the normal force on our car is just equal to the weight of the car. Right? The magnitude of the normal force is equal to the magnitude of our weight. And so using this information, we can actually calculate the static frictional force on our car. So that's equal to the coefficient of static friction times our normal force. But we also know that the circular motion needs a centripetal centripetal force, right? So we know that this is equal to the mass times V max squared divided by R. So we're trying to find how fast this car can go under two different conditions, right? When the road is dry and when the road is icy. So in our case, the centripetal force is going to be given by the static frictional force pointing towards the center. So we have US times Fn on the left. And on the right, we have our centripetal force, which looks like this. Right. And now we can plug in our result for the normal force onto the left-hand side. So notice that left-hand side becomes coefficient of static friction times the mass times g. And on the right-hand side, that's the mass times our max speed squared divided by r. So the masses actually cancel out because it's the same mass on both sides, the mass of the car. So again, we're looking for the maximum speed that this car can go without, slipping off the track, which is given by this equation here. So what I'm going to do, I'm going to multiply both sides by r, and then take the square root of both sides to get V max by itself. So when we do that, we get that the max speed that this car can travel around this circular track is equal to coefficient of static friction times g times r, all under the square root. Right? And so now we have two different conditions. So we have, for dry weather, right, we're using a coefficient of static friction of 0.95. And in this case, the fastest we can go around this circular track is equal to the square root of u sub s, which is 0.95, times g, which is 9.8 meters per second squared. And then we have r. So our R value is 51 meters because that's the radius of this track. Let me take the square root of all this. So we get a Vmax for dry weather, right, how fast we can go without slipping in dry weather, of 22 meters per second. That's our first answer. Now let's look at icy weather. Right, and under icy conditions, apparently, our coefficient of static friction is just 0.1. So plugging that in, we have the max speed that our car can go around this track, under icy conditions is coefficient of static friction times our acceleration due to gravity times the radius of our track. So those haven't changed. And when we take the square root of all this, we see that the maximum speed we can drive around this track without slipping under icy conditions is 7.1 meters per second. So pretty much 3 times slower. So this is a nice little segue to banked curbs with no friction. So let me just banked curbs with no friction. So we're ignoring the possibility of friction for now. And to really demonstrate this, I am going to try to draw a picture. So bear with me for a second. All right, so this is our banked incline, and we have our road. It's kind of like this. And so on our road, we have our car. So expertly draws a box. Right, it's going around this curve like so. And supposedly the center of this circular curve is over here. This is a radius of r. And so a banked curve is quite literally a curve that's banked. So it's a curve that's kind of at an incline. You guys have ever watched NASCAR? So at the end of the tracks, the track itself is actually curved upwards, sort of like this, because that gives the car more traction and allows them to go around faster. So we make a free body diagram of this. So we'll get this from the side. We've got this. This is our circular track, let's say. Here's the center. And then gotta sort of draw something like this. This is our inclined bank. This one is a very steep incline. Just ignore that. So this is theta. So this is going to be a side view of our track. And so we're going to have a car like right here. We're going to call it a box. And so there's some forces acting on our car, right? So from this ramp, there's the normal force points perpendicular to the slope of the inclined plane, so the normal force. But there's also the weight points straight down, right, mg. And so without any friction, these are the only 2 forces that we have. I'm going to choose an unconventional coordinate system for this picture. This is the radius of our track right here. And the coordinate system I'm going to choose. So in the past, I told you guys that whenever you're doing stuff like this, you should, in general, choose a coordinate system that for an inclined plane goes up the slope or is parallel to the slope, and a y component that is perpendicular to the slope. But in this case, it's going to be advantageous if we choose a coordinate system that is what we're sort of used to, right? Where x goes in the x direction in the horizontal direction, and then y is in the vertical direction. And so when we do this, we notice that this angle theta here, right, the angle of our incline, is also going to be equal to this angle theta here, right, between our positive y axis and Fn. And when we do this, we get a triangle looks sort of like this. So I'm actually going to bring that down a bit. So right now I'm just taking this triangle here and I'm going to bring it down. So this is our triangle. Right, so this is our angle theta. Right, the length of this has a magnitude of Fn. And so notice that this part here up top, this is going to be the x component for our normal force vector, right? And then this part here, this green part, is going to be our y component for our vector. So the reason why I bring that up is because there's a component of our normal force that points in the x direction, right? So the x component of our normal force is going to be pointing towards the center of our circle. In this particular case, the thing that is providing the centripetal force for our problem is this x component for our normal force. And so in this case, the x component, the magnitude of the x component, so we'll call that Fnx. The magnitude of this is given by the magnitude Fn multiplied by sine of this angle theta. Right? Just based on this triangle that we've created here. So the reason why I bring this up is because this x component for our normal force is going to be the centripetal force that keeps our car from, sliding up or sliding down. It keeps it in uniform circular motion. So the magnitude for centripetal force is equal to the magnitude for the x component of our normal force, right? Absolute value, if you want to call it. So this is going to be equal to Fn times sine of theta. But the centripetal force is also just the mass of the car times the speed of the car squared divided by the radius of the track. So this bit here, right, I'm going to call equation 1. So now if we're looking at stuff in the y direction, so the sum of the forces in the y direction, right, that's going to be equal to the mass of a car times the net acceleration of the car in the y direction, right? But we don't want the car accelerating in this y direction, right? We don't want it leaving the track. We also don't want it sinking into the track. So we want the acceleration in the y direction to still be 0 newtons. And then the left-hand side is the sum of all of our forces in the y direction. Well, there's only 2 forces that have components in the y direction, which is convenient because our problem only has 2 forces, right? So it's the y component for our normal force, and it's also the weight. So the y component for our normal force points up. So this is going to be Fn times, in this case, right? It's going to be cosine of theta. And I know I told you guys that whenever we're doing stuff like this, I want to typically use angles that start from the positive x-axis and then hit our vector, right? But in this case, I'm trying to be very explicit by showing you the exact triangle that we're using and doing the calculations that way. So this will be the only time where I will, calculate our angle thetas like this, where now x is, given on sines and our y's are given by cosines. So that's the only time I'll do stuff like this. This is our x component. This is our y component. Right. So the sum of the forces in the y direction, we have the y component for our normal force pointing up, and we have the weight mg pointing down, and all that's supposed to be equal to 0. So So solving this, we have that the normal force times cosine theta, that's going to be equal to mg. And I'm going to call this equation right here, I'm going to call this, I don't know why I did that, I'm going to call this equation 2. So now what I'm going to do, I'm going to take equation 1, and I'm going to divide it by equation 2. And so when we do that, we get, up top we have equation 1. It says that normal force times sine of theta. All right, on the left-hand side, just dividing up the left-hand side stuff. So that's Fn cosine theta. And then we divide the two things on the right-hand side. So we have mv squared over r. And for equation 2, we have just mg. So in this case, the m's cancel out, the normal forces cancel out. And then we have sine divided by cosine, which if you know a little bit of trig, sine over cosine is tangent. So this is equal to tangent of theta. It's going to be equal to v squared over rg. So don't worry, this is only a derivation. Stuff like this, when it appears on an exam, if it appears on an exam, I haven't really made up my mind yet, but I will give you guys this equation on the equation sheet. You won't have to remember this. You won't have to rederive it in a way that we were doing. I just wanted to go through the derivation so you see where this kind of comes from. So let's look at a problem, a little example. So the last example was, I think, example 3, example 4. Okay, so now we're on example 5. So example 5. So example 5 says that a car is turning on a frictionless banked curve. A car is turning on a frictionless banked curve. Frictionless banked curve with an inclined angle of theta equal to 30 degrees and a radius of 5 meters. The problem's asking, find the velocity of the car such that it does not skid around. So we don't want it sliding at all. So find velocity of the car such that it does not slide. Right. So we're going to use the result from earlier to help us out with this. So we're basically going to solve this equation right here for v. So if I multiply both sides by rg, we get that on the left-hand side we have r times g times tangent of theta. Then on the right-hand side we have our speed squared. So then if we take the square root of both sides, we get that the speed that we can travel around this banked curve without slipping is equal to square root of rg times tangent of theta. Okay. So now we just gotta plug some things in. So the max speed, we can go around this curve without slipping. It's equal to the square root of r, so radius of 5 meters. G is 9.8 meters per second squared, times tangent of our incline, which in this case is 30 degrees. And we're taking the square root of all of that. So when we do this, we get that the max speed that we can go around this incline is 28.3 meters per second. So to put this in perspective, right, what if our speed v was less than, the speed that we just found? What was it? What if it was less than 23 or 28.3 meters per second? Well, in that case, the car would slide inwards, right? It's not going fast enough. It would slide down the inclined bank, right? And so you can ask the opposite question: what if it was going faster than that 28.3 meters per second that we found? So in this case, it'll slide up. It'll slide upwards. So the very last section I want to talk about today is about satellites in circular orbits. So this is an example of uniform circular motion, right? And when I talk about satellites, I don't necessarily mean, the technological things we put up into, low Earth orbit. I'm talking about things that orbit other things. So satellites in circular orbits. Right, so an example of a satellite would be like the Earth's moon going around the Earth. The Earth is a satellite to the sun, right? Because the Earth orbits the sun. There's only one speed that a satellite can have. So there is only one speed a satellite can have if the satellite is to remain in an orbit with a fixed radius. Orbit with a fixed radius. Right? So that makes sense, right? If we write down the speed of an object undergoing uniform circular motion, then if you have a satellite that is going through uniform circular motion, then its speed is given by 2 pi r, right, the radius of its circular motion, divided by the time it takes for the satellite to make one full orbit around its, whatever it's orbiting, right? And so what this is saying is that if you were to go any faster, if the moon were to travel any faster around the Earth, then what would happen is the radius would have to change to compensate that. So when we're talking about satellites and things that typically deal with gravity, in that case, the centripetal force is given by the gravitational force between the two objects, right? Which, if you remember, is just Newton's constant g times, in this case, we're talking about the mass of the Earth, so that's me times whatever mass we're looking at, divided by the distance between, the center of the Earth and whatever we're looking at squared. But the centripetal acceleration, or the centripetal force, is also given by the mass times the centripetal acceleration, just like this. All right, so this r is exactly the same as this r that appears on the left-hand side. And so if I solve this equation for v, right, notice that the masses cancel out, the little masses, since they refer to the same thing. And then if we multiply both sides by r, this r gets canceled with one of these r's. And so we have on one side that the speed of our satellite squared is going to be equal to g times the mass of the Earth divided by the radius, which is, the distance between the center of the Earth and the thing that's orbiting the Earth. So again, this is a very Earth-centric definition. If instead we weren't talking about the Earth, we were talking about, some other planet or some star or something, then this larger mass m here would be the mass of whatever that object is. right? If we're talking about things orbiting the sun, then this mass here would be the mass of the sun, and r would then be the distance between, the object that's orbiting the sun and our, the center of the sun. So taking the square root of both sides, we see that this unique speed is given by the square root gm over r. I'm going to take the square root of both sides. So for our final example of the day, we're going to put this to use. So this is example, I think 6. Yeah, example 6. So example 6. So example 6 says, to determine the speed of the Hubble Space Telescope, determine the speed of the Hubble Space Telescope, orbiting at a height, of 598 kilometers, 598 kilometers above the Earth's surface. So above the Earth's surface. Right. So the radius that we're going to input into our problem here is the distance from the center of the Earth to our rotating or our orbiting object, which in this case is the Hubble Space Telescope. And so that total radius is the radius of the Earth plus, this additional height above the Earth. So the radius of the Earth is about 6.38 times 10 to the 6 meters. And our height above the Earth is 0.598 times 10 to the 6 meters, right, where I've already converted it from kilometers to meters. And so we get a radius r of 6.98 times 10 to the 6 meters. So that's our radius there. And so the last piece of information that we need is the mass of the Earth. So the mass of the Earth is, it's about 6 times 10 to the 24 kilograms, but the problem wants us to use a value of 5.98 times 10 to the 24 kilograms for the mass of the Earth. Just as a reminder, G, Newton's constant, is going to be 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared. So this value here is actually pretty important. Should have highlighted it earlier. This is the main result from that part of the section. So if we want to figure out the speed of the Hubble Space Telescope, it's going to be equal to the square root of the mass of the Earth, 5.98 times 10 to 24 kilograms, times the Newton's constant G, so 6.67 to the negative 11. There's some units. Right, all that is divided by the radius. There we go. Of 6.98 times 10 to the 6 meters. And all of that is under the square root sign. And so when you punch this into a calculator, get a velocity, right, So the velocity of, or the speed of this thing going around the Earth is 7.56 times 10 to the third meters per second. So this is also like 16,900 miles per hour. So, or miles per hour. Right? It's going pretty fast. And so with that, we've completed our lecture. So I'll see you guys tomorrow.